Hi guys, my name is Amato Day. I'm a Gen Chem 113 lab TA. I'm going to be telling you guys about how glassware is used in lab investigation. So what you see here are the pieces of equipment that you're going to need for the lab. Starting to the right we have the burette, and then we have a beaker, 600 milliliter, then a 50 ml beaker. We got our food coloring solution in sand, a graduated cylinder. We got a scale and weighing boats. And we also have a graduated pipette and a serological pipette. So for part one of the lab, your students will be determining precision and accuracy by using different pieces of lab equipment to measure the densities of water and calculating it and then comparing it to the literature value. So for the first step of this experiment, your students will be measuring the piece of glassware that they're going to be weighing the water in. As so, here is a 50 milliliter beaker, and I'm going to place it onto the scale. So first, obviously, turn on the scale. Place the beaker on. Wow. So here's a 50 milliliter beaker. I place it on the scale. Wait until it completely stops and then hit tare, but record that number that you also got, 30 milliliters of water. So now we're going to fill up the beaker with 30 milliliters of water. Right up to the line. And we're going to go back to the scale. Place it on the scale and record that measurement. So, as with all things in science, you can never measure everything perfectly. So, I did say that I was going to measure 30 milliliters of water. However, if you look at the beaker when you set it on a flat surface, you can see that the meniscus is actually less than 30. So one should estimate to the next decimal place. So what I would estimate for this is probably about 28.3 milliliters of water. So now it is time to calculate the density of water that we measured. So the first thing is I referenced the density equals mass over volume equation. This is the equation that you will use in order to calculate the density. What you need to use are the mass of your beaker with water, and you must subtract the mass of the beaker that you weighed in the first step. This will give you the mass of water that you measured. And you are going to divide that by the volume of water that you also measured in the previous step, and that will give you your density. So here in this bottom row, I subtracted the mass of my beaker with water, which was 56.37 grams, minus the mass of my beaker, 29.97 grams, and I divided that by my measured volume of water, which was 28.3 milliliters, and I got a density of 0.933 grams per milliliter. So what we did for the next step is we measured the temperature of the water, because the density of water varies based on different temperatures. And you can see here that the temperature of the water is at a cool 25 degrees Celsius. And so looking up the literature value of the density of water at 25 degrees Celsius, you get a value of 0.997 grams per milliliter. So now it's time to measure how accurate the beaker measured the water that we're used to. Oh my gosh. So now we're going to see how accurately, hint, accuracy and precision. So now we're going to see how accurately the beaker measured our density of water. If you come here and look at the formula for percent error, you get the accepted value minus the experimental value in an absolute value equation over the accepted value times 100, and that will give you your percent error. So I went ahead and we found the literature value previously for 25 degrees Celsius water as to be 0.997 grams per milliliter. And our experimental value that we calculated based on our measurements was 0.933 grams per milliliter. So if you plug those into the equation, 0.997 grams per milliliter minus 0.933 grams per milliliter over our accepted value of 0.997 grams per milliliter of water times 100 will give you a 6.4% error. So you're going to repeat the previous procedure that we did using the 10 milliliter graduated cylinder, and you're also going to use it with the burette. I want to go a little bit more into how you will measure it using the burette. So lucky for us, we already measured the mass of this beaker. So it makes life easy for us. We don't have to do that again. Instead, what we'll do is we'll place it under the burette and we will dispense water from the burette into the beaker. But the trick is now we're going to use the burette to measure how much water we are dispensing instead of eyeing from the beaker. So we are going to use a 50 milliliter glass burette. If you come here and look at how the burette measures, it goes from top to bottom. So the most accurate way of measuring how much water we are dispensing is to write down the starting volume of water that is listed and then dispense the amount of water that you want and subtract it from your final volume that is listed. And that is the most accurate way of measuring how much water you dispensed. So the way that we dispense the water from the glass burette is using this thing called a stopcock. So the way to dispense water from the glass burette is using this thing called a stopcock. And so what you will do is you will grab the stopcock. Very funny. Okay. Oh, yes. So the way to dispense water from the glass burette is using the stopcock. So what we're going to do is we're going to turn the stopcock slightly to the right, and we're going to slowly dispense the water. And you can see how the volume of water is just dropping the longer I leave the stopcock turned. And then when I turn the stopcock to close it, you can see the meniscus right here on the glass burette. And you can see the meniscus. And we can calculate the end point and subtract it from our starting point. The final piece of equipment that we'll be using to measure the water is using a graduated pipette and a serological pipetter. The way that we use this is by placing the serological pipetter on top of the graduated pipette and slightly turning just enough to situate it so it doesn't fall. Then you will place the graduated pipette into the water, and here you have this dial, this wheel that you'll turn. And all you do is you just push down and the water will come up. And then in order to dispense it out of the graduated pipette, you'll just go the opposite direction. So the objective of part 2 of the experiment is to develop a conversion factor for figuring out how many drops of water it takes to make 1 milliliter of volume of water. And the way we're going to do that is by using the density equals mass over volume equation. Using our accepted literature value of 0.997 grams per milliliter of water, we're going to set that equal to the mass of 1 drop of water, which we will measure on the scale over there. And then we are going to find X, which is our volume of 1 drop of water. And using that volume of 1 drop, then all it is just finding a multiplication factor that can get us to a whole mil of water. And so now we are going to use the scale. Again, we are going to turn the scale on and wait for it to zero out. And I'm going to place the weighing boat onto the scale. And I'm going to write down that mass of the weighing boat and then tare. Next, I'm going to take my pipette and I'm going to just measure, an amount of water. And I'm going to place just one drop onto the weighing boat. And I got a mass of 0.04 grams. So, now we found our mass of one drop of water. And so I went ahead and I calculated the volume of one drop of water using the density equals mass over volume equation. So density equals mass over volume, and we said that we were going to take our accepted literature value, and we're going to take the mass of one drop of water and find x, which is our volume of one drop. So when I plug those numbers in, I had 0.04 grams of water, and our density is 0.997 grams per milliliter. So when I plug it into the equation, I get an x value of 0.04 milliliters. Look at that 1-to-1 ratio. It's nice, isn't it? Now I'm going to find out how many drops are in 1 milliliter of water. And I'm going to use that, I'm going to find that using an equation of volume equals mass times volume. And so 1 milliliter equals 0.04 times x, where x equals the number of drops. And so when I solve for x, I get 25 drops of water. So now we're going to move on to part 4 of the experiment. And this objective for this experiment is to calculate how much volume of an original starting stock dye solution we'll need to use in order to create 3 different 10 milliliter dilutions of the dye. And the way we're going to do that is by using an equation called M1V1 equals M2V2. Now this is the first time students will get exposed to this equation. So it's important that you explain this properly to them in order for them to be able to use it on future experiments, for their future science courses, and even in their lab final exam. I'm sure there might be a problem or two on there. So the first thing that we will do is we are going to look at our stock dye solution, which is at 1.5 molar, and this is our food coloring. And so I'm going to write that down. My M1 is 1.5 molar. My V1, this is what we are trying to calculate. And M2, our second concentration, is listed on the protocol. And the concentrations that we want to find are 0.3 molar, 0.75 molar, and 1.35 molar. So I'm going to use the 0.3 molar as an example, and you're just going to repeat these calculations using the other two dilutions. And our volume 2 is going to be 10 milliliters. We want a total solution of 10 milliliters. So let's go ahead and calculate this. Here I have the equation M1V1 equals M2V2. And I plugged in M1 as 1.5 molar times V1, which is our unknown, equals 0.3 molar times 10 milliliters of total stock solution. Now, I get 1.5 V1 equals 3, and when you solve for V1, you get 2 milliliters. Now, keep in mind that we are having a total volume of 10 milliliters, but we are adding 2 milliliters of the dye solution. Whenever you're making a dilution, you have to always make sure that you are subtracting the amount of your V1 from the total volume of V2. And we're just going to add 8 mils of water, because 10 mils of total solution minus 2 milliliters of the dye equals 8 mils of water. Okay, so now we are going to go ahead and practice how to measure out food coloring and make our dilution. Now keep in mind that we're going to have this stock bottle in the back. And so your students, make sure that you tell them to get a small beaker and just fill it with a small volume of dye and take it back to their table. And I will do just so. So I'm going to pour just a little bit so as not to waste the dye. And we're going to be doing a few trials of this. Keep that in mind. We're going to be doing the 0.3 molar, the 0.75, and we're going to have the 1.35 molar as well. So you want to have a little bit more dye, that way you can just continue taking out volumes as needed. So if we go back here, I'm going to take out, using my graduated pipette, I'm going to take out 2 milliliters of the dye. So there you have 2 milliliters. That was 1. Sorry guys. Now we have 2 milliliters. And I'm going to dispense this into the 10 milliliter graduated cylinder. And all you will do from there is take up from our beaker of water, we're just going to take up 8 milliliters of water because we need to fill it up to the 10. So here I've taken 8 milliliters of water, and now I'm going to dispense it into the graduated cylinder, and it should fill up to the 10 milliliter mark. Look at that meniscus. So that was how you can calculate the first dilution, and then for the next 2 dilutions you're going to follow the exact same procedure using M1 V1 equals M2 V2, and then measuring it using a graduated pipette. I hope that this video helped you in learning how to use lap glassware and how to teach it to your students.